travel, in space and closer to home, made possible by aerospace engineers. Bridges, old and new, conceived by structural engineers. Hydroelectric projects, river locks and dams, combining the skills of electrical, civil, and mechanical engineers. Sewage treatment and waste management for environmental protection. Highways, necessities we depend on every day. Designed, constructed, and maintained with teamwork between the public and engineers. Government engineers in public service. Public service engineers are the human link between every American and their roads, bridges, airports, and countless other parts of our infrastructure.
One of the roles of government engineers is to really be the watchdogs for our society.
Public service carries a responsibility for the integrity of these projects while protecting the public's safety and economic welfare. The public relies on government engineers in ways they probably don't even realize.
If you didn't have engineers, you wouldn't have a warm home, you wouldn't have electricity, you wouldn't have telephones and televisions and roads to drive on, and so every aspect of our life is affected by engineers.
If you're going to build a building, the public has to be sure that that building is going to stand up. If you're going to build a bridge or a highway or whatever, and that's why engineers exist.
Engineering is a matter of solving problems.
So we like to think that when we're doing our jobs right, we're trying to save people's lives.
Federal, state, and local government engineers are involved in all phases of public works. They're professionals. We rely on their education, skills, and ethical judgments. From the aerial rigging of wilderness electric lines to designing and building flood control projects, engineers are improving our national highways and waterways and enhancing military aeronautics. Their impact is wide-ranging. From a major highway project in Seattle to a flood control plan in San Antonio to a network of underground cables which provide security for a hillside neighborhood in Cincinnati. From ensuring state-of-the-art wastewater treatment in Kentucky to finding better ways of dealing with solid waste in Columbus, Ohio. Government engineers are working to improve the quality of all of our lives. Completing a mammoth project like the new Mississippi River Lock and Dam number 26 represents hard work and coordination. For the government engineer in charge, it's a source of personal satisfaction.
Personally, I like to see things being built. And where better can I see it being built in some project like this one? It's not very many engineers that get to oversee a billion-dollar project.
This new 1,200-foot lock will allow barges to pass at a rate 4 times faster than existing locks. This means lower transportation costs, costs that are paid by American consumers. From the initial design through final opening of the locks, government engineers have been critical to the entire process.
You have to have engineers to do the design. Then once you spill over and have with the design done into construction, you have to have engineers at that point to understand the design and make sure that we're getting the product that we've specified.
While this mighty river is undergoing massive changes, a much smaller waterway which runs through San Antonio also promises to have a major impact. Throughout most of modern history, San Antonio has been plagued by periodic flooding, which has resulted in substantial loss in lives and property. The project was conceived as a flood control effort, but it has also become a scenic calling card for the city. Dorian French is the chief engineer of the river.
Over the past 30-some-odd years, we've constructed 30 miles plus of flood control channel up to and through the central business district of San Antonio.
Far below the downtown business district, huge tunnels will help pass floodwaters safely beneath the city. River Authority engineers use the latest design technologies to plan and build these canals.
As engineers and as a governmental entity, we're involved with the design, the construction administration, surveying, all the different civil engineering aspects of putting a project out on the street and getting it built.
While the lives of Texas residents are being made safer, Commuters and visitors to Seattle are benefiting from a major highway project, which is breaking new ground in construction technology. The $1.5 billion I-90 project is distinctive because of its size and complexity.
We've got a lot of unique features, like floating bridge, the largest tunnel in the world that's in soft earth. We've got two very large lids, which are basically cut and cover tunnels. Those are each about 3,000 feet long. On Mercer Island, also, the project is to be more or less out of sight. So it's 30 feet below original ground and generally out of view of the local people.
Completion of this project requires working with a number of different political and construction entities. It wouldn't have been possible without government engineers. With 15 major contracts going at once, the job of project management has been immense. Computer scheduling techniques were used to track many pieces of this complex construction puzzle. I-90 passes through an existing highway corridor, so construction had to proceed with minimal impact on traffic. Environmental concerns of local citizens have been answered by many design elements. Parks and bike paths which hide 8 lanes of traffic and thousands of cars. Huge ventilators that rapidly exhaust the tunnel air. A control center which constantly monitors traffic from several vantage points. Project manager Bill Dews views his role in this multifaceted project with excitement.
I think the most exciting thing is the coordination and cooperation from so vast many groups, not only the state engineers and the federal government engineers, but the local engineers with the cities and the communities and the contractors. Everybody with different and sometimes competing interests, yet coming together to accomplish this program.
While many different government engineers are involved in new construction, sometimes they are also called upon when something goes wrong. Several years ago, Cincinnati residents looked to government engineers for solutions when their neighborhood unexpectedly began to slide downhill. Despite extensive pre-construction testing, highway work nearby had caused this hillside to shift. Homes and streets developed cracks. Construction stopped, and 30 families had to move out. Government engineers faced a double dilemma: how to finish the highway project and how to prevent further slipping. Engineers developed a plan to hold the hillside in place with a system of heavy gauge wires which run through the hill from top to bottom. This wall anchors the hillside with 161 concrete cylinders set deep in the ground. Wire strands which run through the hillside are measured periodically for stress. After several years, they've stood the test of time. Government engineers are frequently called upon in emergency situations, like the time the historic Roebling Suspension Bridge linking Ohio and Kentucky began to sway. The weight of hundreds of football fans walking one way and heavy buses traveling in the opposite direction caused some nervous moments for people on the bridge.
Balance. When I looked up, it was rhythmic. It was very definitely rhythmic.
The bridge was closed that night until it stopped swaying. People relied on Kentucky state engineers like Richard Sutherland to answer the question, is this bridge safe?
If the bridge had moved sideways, we knew that we could be in for some big trouble because it's not designed to move sideways.
Equipment was brought in to thoroughly test the bridge.
The diagnosis of the problem was that we had sustained what's known as harmonic motion of the structure, which is a rhythmic movement that occurs in all structure.
Testing determined this historic structure was responding within its design limits to an unusual stress that was not likely to recur. In 1867, when this bridge was built, buses and hordes of football fans were probably not anticipated. But by thoroughly studying the structure with the proper engineering approach, the answer was found. The bridge was declared safe and has not swayed since. The responsibility of protecting public safety is one Richard Sutherland takes very seriously.
Whether it's your relative or somebody you know or somebody you don't know is out there traveling, and that decision that you made is going to determine whether or not he gets home safely. A great deal of responsibility goes along with that, and a great deal of liability goes along with that, but it's one of the things that an engineering government can get satisfaction from. It gives you a good feeling to know that you've done your job well.
Several thousand miles away, technology is providing a new answer with a modern-day drawbridge, or in this case, a swing bridge. The second phase of the West Seattle Freeway project features the world's first hydraulic double-leaf swing bridge. When completed, the bridge will allow local traffic to move about this industrial area while providing ships access to the harbor. Each side will swing away to allow river traffic to pass.
The leaves would rise on command and would swivel in this manner so that the waterway is open and the ships can go through, and then close back up and set back down.
It's quite a challenge for the city engineering department, but after completing the first phase, these government engineers have shown they're up to the challenge. Phase 1 was a 6-span high-level freeway bridge, which cost $150 million. It was completed ahead of schedule and within budget. Keeping our rivers clean is a major challenge facing environmental engineers. The Morris Foreman wastewater treatment plant in Louisville, Kentucky, provides a case study in the struggle to apply new water treatment technologies. There have been hard lessons along the way. This plant was built in the 1950s. In the 70s, the federal government required more stringent wastewater treatment methods. This plant was having trouble meeting the new environmental standards. Gordon Garner was the professional engineer who was brought in to head the local agency. Garner worked in an administrative capacity to oversee its redesign. He's credited with turning plant performance around. Critical to his administrative success is a background in education in engineering.
Well, the reason why engineers need to be in the key administrative positions in public works agencies is because you have to understand the technology of what's going on. You have to be able to know when somebody is making the correct judgment and the correct technical decision about what to do.
The challenge of improving water quality is matched by concerns over solid waste. Every day, our society is creating more and more trash, and we're running out of space. One solution is the trash-to-energy plant. Columbus, Ohio was one of the first cities to build such a plant. Here, refuse is shredded and burned to create energy, which Columbus uses to light its streets.
One of the first roles of the government engineer in the development of this project was actually conceiving the project. It was recognized that there was a need to reduce the volume of trash to extend the life of our landfill.
The plant is designed to burn 2,000 tons of solid waste daily. That increases the life of the landfill by a factor of 7. After design and construction, the responsibility for efficient operation remains in the hands of government engineers.
We as engineers are really the only people left with that chore, really the only people that can accomplish that chore. We have the technology, we have the know-how in order to be able to address both the economics of operation as well as the environmentally safe ways of getting rid of trash.
Many other cities are building these types of plants. They all benefit from the lessons learned here. Government engineers can get into some pretty exciting jobs. Engineers who work for our U.S. military fulfill functions vital to our national defense. Captain David Legg took the cockpit section of a T-38 jet, designed a computer program to go along with it, and built a flight simulator from the ground up.
They keep it on this heading if you can. Let's accelerate up. Okay, we got full afterburners, looking good.
The simulator is used to help military investigators find the cause of airplane crashes.
Oftentimes we're trying to answer questions about what if this had happened. If a pilot had pulled up sooner, or if the bird hadn't hit his airplane, or something of that sort. And we can recreate all those things in here. We can take things off the airplane, we can put things on, we can do damages just by reprogramming the computer code that we designed.
Another government engineer is putting his college background in structural and aerospace engineering to the test. Eli Kolyas is working with computer modeling to diagnose the cause of fatigue cracks in military aircraft wings.
And what we have to do is try and predict where to look for this cracking. And if we see problems, we want to model that. And we use these computer techniques, and it's a lot of mathematics involved, in order to make a prediction. So it's a mathematical approximation of a real structure.
Many engineers look to space as the last great frontier, a place to push the envelope of new technology. For some government engineers, the dream of becoming an astronaut is the biggest dream of all. For engineer Jan Davis, that dream is reality. Before being chosen as a mission specialist and undergoing intensive training as an astronaut, Jan Davis built a distinguished career in government engineering. She was team leader for structural analysis for the Hubble Space Telescope. She was later named lead engineer for the redesign of the solid rocket booster external tank attach ring.
My specific background in mechanical engineering really helps me to understand the space shuttle that we're flying on, which is a complex vehicle, and we have to understand all of the systems and how they work, which means hydraulic system, electrical system, computer systems, environmental control, data systems. And so in the case of a malfunction or if we lose communication with the ground, we as astronauts have to be able to understand the system and understand what's going wrong and how to troubleshoot it.
As an astronaut engineer, Jan Davis will be instrumental in developing future technologies through research in space. She believes her job experience and her PhD helped, but there was more.
I think I represent more than anything that hard work and perseverance pays off because I've had setbacks in my life on my way to becoming an astronaut, but I had a goal and I worked hard to attain it despite other obstacles that I had and that other people put in front of me. So it's just a matter of having a dream and setting a goal and working hard to attain it.
Government engineering is important work, and it's becoming more important every day. From the roads we drive, the bridges we cross, the water we drink, the trash we generate, the planes we fly, to the untold discoveries that await us in space, government engineers work to improve the quality of our lives and to keep us safe. Guided by a professional code of ethics, government engineers stand for integrity, technology, and the prudent spending of public dollars. Their roles in designing, constructing, and maintaining the public works we may take for granted provide them with interesting challenges in the years to come. They will provide us with continued improvement in the quality of our lives.